Okay, so that's the plan for today. We're going to talk about, we are going to first to start with an exercise to calculate pressure and temperature drop in pipeline. It's a 75-kilometer pipeline and it carries oil. And this oil is not completely stabilized, but it has a very low GOR. So we are able to use this conversion between BO to calculate the local rate. So we practice that. And also temperature, we see the effect of how does it affect viscosity. And we are going to take that into account. And then we are going to start on multiphase. That's the introduction on multiphase, basically in tubing. And then we will stay with multiphase hopefully by the next 3 days. We will talk about today generalities. Tomorrow it will be nomenclature. On Thursday will be integration methods, and we'll see if we have time on Friday to do something on correlation. Okay, so just a refreshment from last class. I told you that we made a very big assumption when we were calculating the this well when we made the IPR and TPR intersection. We made a very big assumption. We say local rate is equal to standard condition rate. And I told you that's only true if really the oil is extremely incompressible and actually also doesn't release any vapor. No vapor comes out, gas comes out of solution. But usually most oils, when they are taken to surface, they release some gas, comes out of solution, and then you have to take that into account. The fact that the volume rate is much smaller than actually the local rate. And that we do with a factor called BO. And this BO, I told you how we can estimate in the undersaturated region. That means if P is above the bubble point, we use this exponential function that basically depends on CO, that we are going to use a correlation, the oil compressibility by Vasquez and Bex. We're going to use the bubble point pressure, and that's by standing. And we're going to use also the oil volume factor at the bubble point, and that's also another correlation by standing. Okay, all of these are expressions. And I told you this was done for, or has been done, or is still done for many areas in the world. Some people do it for the North Sea, some people do it for Gulf of Mexico, some people do it for onshore US, some people do it for South America, Colombia, some people do it for the Middle East, etc. Okay, so you can find correlations, all kind of expressions that give you, but basically they are all of them are some more or less based on something that represents the composition of the oil and the composition of the gas at standard conditions, and that's the specific gravity. The GOR, to see how these two you mix them together. If you have more gas, you will have something that vaporizes at a very high pressure. But if you have less gas, then it will take a lower pressure to vaporize. And then the pressure and temperature, depending on which pressure you have and temperature you have. Okay, so we are going to use these particular things to calculate BO. And then I told you that viscosity actually has a similar behavior with pressure, that it goes down first because when the gas starts to come inside the oil, then it makes it a bit less viscous. Okay, but then after that, when you increase the pressure, then actually the pressure is making compacting more the molecules against each other, and that makes the viscosity higher. But I told you that really we are going to neglect in this exercise the effect of pressure because that increase, maybe this is, if we say here this is maybe 2000 psi, this increase might be of 1 centipoise, which you might say, okay, maybe is important. But when you come to temperature, you see this scale is in log. That means that you have 100, 10, 100, 1000 for every change in temperature. So viscosity affects is much more important the effect of temperature on viscosity than temperature. So what we are going to do in the exercise, actually, we're going to neglect any dependence on pressure, but we are going to say it depends on temperature. So we have to be able to track the temperature along the pipe, to calculate the temperature along the pipe. Okay? And this, I don't have a correlation for that. We're going to use a table, a collection of points, but that gives the opportunity to use a function that actually makes table interpolation. Okay? You don't have a function, but you basically have to interpolate on the table. Okay, so that's the background for the exercise today. So the exercise is, if you open, I gave it last class, but we didn't have time to go through it. But it's called pressure and temperature calculations in horizontal flow line or pipeline. Okay, even my own file is suspicious of me. And we have the field, actually, this is data from a real field. I think this field is called Dulang. It's in the South China Sea. I think it's producing either to Malaysia. I think it's Malaysia. It's the Dulang field. So we are going to analyze. Basically, your task is you are a production engineer. That you have the task to calculate. There are many FPSOs that they have their own wells, FPSOs platforms, that they have their wells, oil wells drilled, and they are producing. Then the production is sent to a central processing unit platform. And from that platform, you have a pipe that goes 75 kilometers to shore. And this is called Dulang. So this is class exercise. And it will also be, I forgot to give you home exercise yesterday. So I guess you're happy, huh? Yes, I forgot. So now you get home exercise, but we don't. I all the time want to give you an exercise so you don't feel alone if you are bored at home. You're just watching TV. You say, "What else can I do with my life?" And then you remember, "Oh, I have an exercise," and you feel happy. If you don't have an exercise, what are you going to think? Oh, now I have to just keep watching TV. Okay, but basically your home exercise will be just the extension of this class exercise. So I suggest you invest time to do it here in class, and then it will be very easy to expand. But basically we're looking at this pipe, and we're going to assume that it's relatively horizontal pipe. Okay, we're going to neglect the inclination. So we have P in and P out, and this is in this place that is difficult to pronounce. Kuala Terengganu. Kuala Terengganu. Again, is producing to a separator that has a constant pressure of, it says here, um, 50 bar. Okay, and we want to calculate if this rate is 100,000 standard barrels per day, and the GOR is very low. I told you, you managed to separate almost all gas, but not all of it. So it's 0.5 standard cubic meter per standard cubic meter. The GOR is here, 0.5, and the temperature is 60. That's the temperature, is 60 degrees Celsius. This is 75 kilometer, and I want to calculate that pressure. What else? Okay, the pipe is, I think, is 16 inch. 16 inch. So note something. What do we want? Okay, in this equation, what do we want? Do we want P1 or P2? we want P1, right? The inlet pressure, the required pressure at the inlet of the pipe. That means, but also, this pipe, the problem is, one thing is that, okay, probably when I plot the pressure versus length, the pressure, here we'll have a value that is high, and then it will go down all the way to 50 bar, right? So in that case, the pressure will be different in every section of the pipe. That means that I will have a different, for each pipe section, I will have a different QO local. Okay, I have the same, for all of them, I have the same QO at standard conditions, which is 100,000. Okay, but I have a different local condition. So I have to compute the BO for each one of them. So the way I suggest, I say split the pipe, and here we're going to make it in intervals. The delta X will be 10 kilometers, okay, 10,000 meters. But you at home, for the home exercise, you're going to use delta X equal to 1,000 meters, okay, 1 kilometer. And you can compare, and you have to compare what is the effect of using a small step or using a big step. And the way we are going to make, so we start from the point that we know, the pressure that we know, and we are going to assume, here we can calculate, we have pressure, but we need to calculate at this point the BO, okay, and we need to calculate the density of the oil, and we need to calculate the viscosity of the oil. And then with all of that, we can compute the delta P of the, let's use another page. Okay, so I have each segment of pipe. Okay, I have here P separator, that is 50. And what I'm going to do is I'm going to say, well, I'm going to calculate the pressure. Let's say that this is pressure 1, 2, 3, 4, pressure 5. Okay, pressure 5 will be equal to pressure of the separator plus the delta P that I calculate in this point, okay, times the gradient. Let's say, let's use it properly. dP over dx times dx. Okay? When this friction factor, remember here I have inside the friction factor, I have the elevation, if I had any elevation, but here inside I have the friction factor that's going to be calculated with the viscosity in P6, the density in 6, and the BO in 6. Okay, so it's like I'm going to assume that all properties for this segment will be, I can use the properties of 6, okay, to go back. Then after I calculate 5, I do the same. I calculate now all properties in 5, and then I calculate 4, and so forth, and I go step by step. There is now a big problem. I need, remember, for BO and all of these properties, this one depends, is a function of temperature, this is a function of BO, and BO is a function of pressure and temperature, right? So I need to have temperature. And the problem with temperature is that I have the temperature actually here in T1, but I don't have the temperature any other place. I don't know what is the temperature of the separator. So I have to have a model that will predict the temperature profile, and then only then, after I have the temperature profile, I can start doing my pressure calculations. Okay, and keep that in mind, because that happens on almost every system, or it will happen very often, that you have pressure in one end and you have temperature in one end, and you have to progress actually in opposite direction. Okay, the temperature calculation has to go like that, and pressure has to go like that. But I will go back to it. So temperature calculations are like that, and pressure, it goes, okay. And this is, you will see now, is not a big issue for liquid, but if you go for gas, it's a, it's a big issue. And then you have to, it's much more demanding, the solving process. I will make a comment after, but just remember, just remind me to make the comment of what happens when we have gas, okay? Because we have to assume, we have to compute, and then we have to see if the value that we assume was actually the value that we have. Okay, so now we need temperature, and this pipe, this particular pipe, if we see the cross section of the pipe, we have, actually this is the ID of the pipe, okay, the internal diameter. Then we have the metal wall. Then we have some plastic, polyurethane or whatever, some that it acts like the insulation layer. And then we have that the pipe is completely unburied. So we have here is just the sea bed. So the sea, we have the seabed, okay? So the fluid and that seabed, the temperature, I had it here someplace, is 14, okay? Sea bottom temperature, relatively warm. So this is a temperature equal to 14. And here I have a temperature of 60, and then I will have heat transfer between them. And be aware, if we look, let's look at we have here the mu that's supposed to be viscosity with temperature, and you see this plot. If we somehow manage to go all the way to 14, okay, that will be a catastrophe. That's why we need insulation, because you see the only already at 20 we have a viscosity of around maybe 2000 centipoise, okay, which is very high. We are usually, for a typical oil, might be something between 1 and 8 or 1 and 4. When we are already talking between 50 and 100, this is a highly viscous fluid. And when we go to 2000 centipoise, then that's just too much. Okay, it will create a huge pressure drop. Okay, so let's put that comment here. At T equal 20, viscosity of the oil is around 2000 centipoise, which is too high. Okay. It will be very difficult to pump. It will require a lot of energy to pump this oil. So to do that, if you remember, we have, we need an energy equation that will tell me how the temperature will change with distance. Okay, we need a temperature equation. But first, I want to remind you. So how do you tackle this example? You define overall heat transfer coefficient, right? A coefficient that will take into account convection of the fluid inside, then conduction in the metal wall, then conduction in the insulation, and then it might be forced convection if you have some marine current flowing on top of the pipe, or you have just free convection that the water is still, and then you have just heat transfer. Yeah, so, and the expression, I'm not going to go into that, but the expression looks something like that. And remember that to define this U, you have to define an area, how you're defined, if it's based on the outer area or if it's based on the inner area. Okay? Because you have to divide by the area. After you have the procedure to calculate this U, is that you have to calculate the heat transfer for convection, the heat transfer, the expression for this conduction, the expression for this conduction, and the expression for this convection. You will have a lot of Q's, Q equal to delta T divided by a coefficient. And then you make all of these Q's are equal, okay, all of these equations are equal, you add them up, and then you define, you will see that all the t's actually are going to cancel each other because they have different sign. Okay, like t, for example, for the first expression you have t fluid. I think I had a figure. Let me check. For the first expression, you will have T fluid minus this temperature, T1, equal to Q divided by a coefficient. Okay. For the other one, you will have T1 minus T2, okay, equal to the same heat transfer because the same heat has to go through all layers. And then T2 minus T3 equal to the same Q divided by another coefficient, and then T3 minus T out equal to Q. And you can add all of them up, and then you're going to get rid of all of these intermediate, and you will get just T fluid minus T out is equal to the same Q, but divided by a big coefficient. And this is what we call the overall, this is the overall heat transfer coefficient. Okay? But you don't have to worry, I have already calculated that for you. So if you're going to calculate the heat coming from the pipe, it will be 2p, um, the radius of out, okay, the radius of 3 times the length of the pipe times this u times T of the fluid minus T of the ambient. Okay, that's how you have to have the outer area times the delta T times this overall heat transfer coefficient, and I have already provided for you the heat transfer coefficient, and it's here, it's 5. Okay, so now let's look how are we going to predict the temperature. So that's very short, but so you just see where the equation came from. Short derivation of temperature equation for liquid flow in pipe. So we have basically this differential equation dq dl equal to dh over dl plus dv dv over dl plus dz over dl times g. Okay, all of that times the mass. Okay, first law of the thermodynamics. Okay, and if it's horizontal, this actually is the derivative of the ratio between the elevation and the length. And if my pipe is horizontal, then this one is 0. So I can remove that. I will assume also that the change in velocity, the kinematic energy is not so important. So I will cancel that. And I end up with this expression that is just dq over dl equal to dh over dl times m. Okay? Then for liquids, you know that this h is equal to cp dt. Okay? So then we end up with dt dl times c times m. And then we have the q, which is the expression we already defined. We make it for a very small segment, which is so q equal to dq equal to dl times was 2p r, I will call it r3 times u times t minus t, that is of the t of the fluid. Okay, I will change now t of the fluid is equal to t ambient. Okay, then I substitute here, and remember here I have to use a convention. There is a convention for work coming out of the control volume and for work coming into the control volume and for heat also. In this case, we are assuming that the heat is coming out, so we have to put a negative number. Yes? So this will be T ambient minus T times 2PR3U. Okay, if I didn't make any mistake. Okay, and then the nice thing about this expression, I'm going to divide everything by this guy here, all expression. So I get T ambient minus T is equal to d dt over dl C m over 2pr3u. Okay, and I have a first order differential equation, I'm going to define A has Cm over 2pr3. Did you see this equation before or not? Okay. Yeah, I will take it because Cp and Cv are the same for liquid. And then we end up with dt over dl times A plus T minus T ambient. Okay, if I didn't make any mistake. Okay, so how do I solve that equation? You have something that is called the factor integrante. Remember that method? You multiply something with all the equation, and then you can make this variable separation. So I'm going to multiply all the equation by e to the power of I think is x or L divided by a. Let's see if it works. Okay, then I get dt over dl e L over a times a plus t e L over a. Okay, did it work or not? I have a small problem someplace. I have to multiply times e a, right? I think so. Okay, because I have, so this one is equivalent to the derivative with respect to length of e L times a times t. Okay, equal to T ambient E L times A. Yes, because I have to derive here the first one, so then that's how I get, without deriving this one, so that's how I get this guy here. No, actually that's not, right? You see what I'm trying to do? I multiply by this factor, and then I try to see that this is the sum of a derivative. But I think I have a mistake someplace. Do you see the mistake? Huh? I think maybe let me try with something else. Let me see if I put this, I leave it without anything. I just put the A here and the A here. Okay, and this one will be 1 over A e to the L, and now I'm going to multiply by L over A. Okay, sorry, but I forgot exactly how is the derivation. Okay, does it make sense now? I divided everything by A, then I multiply everything by L divided by A, and then I say these two guys are equal to the derivative with respect to length of E L over A. So that will give you this guy here times t, or the derivative of t times this one without deriving. Yes? Now it looks like it worked. Now I can do this variable separation, and now I can actually integrate that equation between L1 and L2, and I can integrate this equation also between L1 and L2, and I get T ambient, okay, dx, and d of E L over A times t, okay, that means E, and this L I'm going to say is at a generic L, okay, I want to start exactly from zero, okay, from the beginning of the pipe, and I'm going to say I'm not going to integrate to any particular point L2, but I'm going to integrate just to L, a generic, because remember I want to find the temperature every 10 kilometers. Okay, so at the end I end up with L over A T at L, okay, minus this one will be exactly T at L equals 0. Yes, because the other one, e to the 0, will give you 1. And here I have the integral of that is actually, the integral of the exponential is 1 over a exponential L over a T ambient. Yes? No, right? It's the a should be up here, such that when I derive it, I get exactly that expression. Yes? And now finally, I'm just, don't fall asleep yet. We are just finishing. TL is equal to E L over A of T ambient. Move this one to the other side, so I have minus T plus T. Okay? And then I can take as a common factor this E. Well, I can leave it like that. That's the expression for temperature along the pipe. For a generic distance L, you see that I will have just the temperature at the inlet of the pipe. Well, actually, I think it's nice to, well, actually, there is a mistake here, I think. Yep. So this one should go away, no? This one should go away, right? I think that's the expression. Let's see what do you have in your exercise. So all of that is just to introduce this expression, T E T I minus T by the exponential of L minus A. Okay, just check. I will check it also at home, but that's how you derive the equation. Maybe I made some mistake, but I don't want to spend too much time on that. Okay. Um, and that's the expression actually you have programmed, okay, in VBA. It's called Unburied pipeline TIL. Okay, is the temperature at any position L in the pipe. And you need this A. Which A? Remember, A had inside was the this heat capacity, the mass flow, the outer radius of the pipe, and the heat transfer coefficient. Okay? So everything really in this pipe, if you see about what is making this U, really, I can assume that everything is constant for this pipe. Okay, the internal convection coefficient, the external convection coefficient, the how you say this conductivity of the material, everything will be the same, and also the mass flow. Okay, the mass flow doesn't change. The pipe carries the same mass flow from beginning to end. So really, this equation doesn't depend at all on pressure or doesn't depend on anything else. So it can be computed independently of pressure. I can compute first the temperature, and after I have the temperature, then I can calculate pressure. Okay, which is perfect for my application. Okay, so let's go now to the exercise and use that equation to predict the temperature over the pipe. Okay, so the first one is 60, and here I'm going to say call that, the name was temperature, user defined, unburied, pipeline that is not buried, temperature at any position in the pipe, and I need TE, which is the ambient temperature, is in this case 14, I block it, temperature at the beginning of the pipe, okay, which is the 60, I also block it. The distance at which I'm calculating the temperature, to the left, that one I shouldn't block because I'm going to drag it down. And then this A coefficient that I just computed here for you. Okay, and then I drag it down. And it gives me a problem. I didn't block something. Let's see, what did I didn't block the A. Okay, and now let's see. I get down to 21. Okay, which is going to be dangerous. Let's see. Okay, so I use that equation to compute the temperature along the pipe, and now I want to calculate, now I have everything I need to start calculating pressure. And remember, pressure, we're going to do it actually the other way. We are going to start from the bottom, from the separator, and we're going to go up. Okay, so it's like strange that you go on opposite directions. But let's calculate BO, and BO, for that you have an expression that I made for you to make your life simple. You see here I have BO that depends on the things that the black hole correlation depend, which is the specific gravity of the gas, specific gravity of the oil, the GOR, the pressure, and the temperature. And here you see what it has inside. Basically, it's computing. First, it's changing units because these correlations are made with field units. Okay. Then I'm calculating the bubble point pressure. That correlation is the standing correlation. Then I'm calculating the volume factor, oil volume factor at the bubble point. That's also standing. And then I'm calculating the compressibility. That one is by these Vasquez and Beck's. And then I'm using the expression that I just showed you before, the exponential. Okay, so everything is clear where it came from, I hope. Okay, so let's use that expression. BO, it's called BO, just BO, plain BO. We need the specific gravity of the gas, block it. Specific gravity of the oil, block it. GOR, the GOR was someplace up here or down here, here. Okay, also block it. The pressure, okay, here I have a problem. Okay, the pressure should take the value from here, but it's going to be empty for now. And the temperature, I do have the temperature luckily to the left, and I click OK. And of course, it gives me an error because I don't have a pressure yet, but it should give me a value for this for the first point. You see, for a condition of 50 bar and 21, the value is very close to 1. So everything is almost the same. The standard and the local condition is almost the same. It won't have any difference on my calculation. Then, so let's calculate with that. If you remember, BO was the ratio between volume of oil at local conditions divided by volume of oil at standard conditions. So to get the rate of oil at local conditions is equal to BO times the Q at standard conditions. So let's do that calculation first. Here you have QO, and that will be this number times this the rate. I have it here, okay, in standard cubic meter per day. I block it, standard condition rate. Okay, then I drag it up. It will have an error here because I don't have yet the pressure. Now comes the density. I need the density for the pressure drop to calculate the Reynolds. Okay, so the density, I use that expression that I showed you before, this expression. I have the BO, I have the GOR, so I can calculate very easily. So I'm not sure how I call that expression. Density, I think, is the density of the oil. Specific gravity of oil, specific gravity of gas, that is the GOR. Okay, the GOR is this one, and I have to block all of that. And the BO, take it from here. And here, what happened? Let's see. Okay, B10, B11, B12, and then BO will be here. Okay, and actually I got a density 747. That's relatively very light crude. And of course I have error here. So now I still need one more thing for the pressure drop calculations, and that's the viscosity. Okay, and the viscosity, we're going to make an interpolation in this table. Actually, we're going to come and say, well, we have now, for example, 21, and we want to interpolate here and say, here you have 21.10, and here you have 20.53, and I want to interpolate between these two numbers. Okay? So for that, I also prepared a function for you that makes the interpolation automatically. And the function is called, you can use it for something else, but it's table interpolation. You give the value of temperature that you want, okay, in this case 21. You give the column where your data is located, if it's in the first column or on the second column or the third column, and you give the matrix where it should interpolate. Okay, so let's do it here. We say that viscosity is equal to table interpolation. Value, remember first the value that I want to interpolate, temperature, then the column where the information I want is, that is, if we look at the table, is column 1 and column 2. Will be in column 2. That's what I want. Okay, table X, comma, column 2, and then I have to give the matrix, and the matrix I just select the whole thing, okay, the whole thing. And I have to block it, of course, because otherwise it will start shifting. Close, enter. Okay. And made it without me going manually trying to interpolate between these points. Okay, this does automatically the work for you. And you can look how it was defined, but that's not the purpose of the exercise. We pull it up, okay, and we get, you see why it was important to cut the pipe in pieces, because the viscosity changes very dramatically in the pipe, okay, from, this is centipoise, okay, so here we should times 1 e to the minus 3. Okay, because that's what we have on the table. It's in centipoise, millipascal, okay, centipoise, And we have then to convert to Pascal times second. That's what we need in our expression. Okay, so I pull it up. Okay, and now finally I come to the pressure, and I told you what do we want. The expression we need is P in, okay, and we have P out, and we have to do that for every segment. Calculate. We have P out. Calculate P in. Now we move up. We have P out. Calculate P in. Move up, and so forth. Okay, so here we say P in. What does it want? It wants the rate will be this rate. Okay, remember we are going to calculate based on the conditions of the previous segment. The inner diameter, I have it here in meters. That one should be blocked. The density from the previous segment, that should be also blocked. Viscosity, the viscosity from the previous segment. Sorry, this one shouldn't be blocked. This one should be changing. Okay, for every segment. Length, the length will be just this one minus the current. Okay. The angle, in this case, is horizontal, so I put 0. P out will be actually the pressure here, 50. And the roughness, I also should block it. Be careful with that. And it's here. Okay, and it says I got 53 pressure drop in that segment, and the roughness should be blocked. Is so much. Then I pull it up, and everything will start to come up. Okay, so now I will say just stop. I found a mistake here. I think I have a better focus when you're not staring at me. So I found that we forgot to take this 1 over a. We didn't take it here, and then that goes away when we do the integral of that. But actually, when x equal to 0, this doesn't go to 0, but e to the 0 is actually 1. Okay, so that's why we were missing that term. E to the 0 is 1, and then we had just t ambient. And just the main point to convey here is that it has an exponential decline, okay, with length for single phase liquid. Now, all of you did the exercise. I'm happy that you managed to do it. And that's what I got. The temperature, as expected, you have this exponential type decline. The equation, that's how the equation looks like. So that's what we should obtain. But you see here, for the example we did before, this was just a constant gradient, okay? That you had, that actually the friction, everything was the same. So you had a gradient, a linear gradient between them. But now, because we are doing it in steps, and actually here you can see I'm doing it in this step. Actually, the steps, they are in this direction, okay? I'm doing first this step, then I'm doing this step, then I'm doing this step, and so forth. And for that, I'm using the properties to assume, I assume that the interval, all of this interval, has the same properties as this node. Then I move to the next node, and then I say, well, all here, they have the same properties that this node. And then I calculate that pressure, and so forth. But here you can see relatively very, very important. And so I ask you, are we going to have wax problems in this pipeline? If you remember the discussion yesterday, there were many things discussed, but one of the things was that in this linear segment, this is the cloud point, right? Or also called WAT, the wax appearance temperature. And that's when we start seeing these small crystals coming out of solution of the wax. Okay? And here we have this pour point. Okay, the temperature we have at the end is around here, like 21, very close. So probably we're going to have a lot of wax deposition in this pipe. So I ask you again, do we need to put two lines then for this pipe? Do we have to put for this that Dulang field. I think it's called Dulang. Did we put the name someplace? Dulang in I think it's Malaysia. Malaysia. Do we need to put two pipes then to make pigging? Yes or no? Not really. We can send the pig that we need in case of subsea systems. We need because we don't have any place to receive the pig, so we have to send it and retrieve it from the same place. But in this case, we can send it from the platform and we can receive it in the separator. Okay, here on land. So we don't need to put two lines. We can use one line, but then as we expect pigging, as we expect wax, then we have to do frequent pigging. And we have to determine how often that has to be. Every month, every 6 months. Remember, it's a big job. I have to basically to stop operations. I have to stop the flow of oil, and then I have to push the pig, and that might take a long time. And every time that I'm not sending oil to shore, I'm losing money. Okay, so and that's something very critical. If it comes an expert and tells me, well, you have to wait, 6 months to pig, and then I wait 6 months, and then I have a big plug that actually plugs my whole pipe, and nothing I can do about it, then I'm in a big problem. If I have another expert that tells me, well, do it every month, then I'm wasting a lot of time that I could be producing. So I have to find what is the real number that I need for my system. What is the maximum I can wait to do pigging without compromising my system? Uh, yes. Now the next thing I wanted to say is that I did, homework also for you, and say what happens if now I have two engineers, okay, or I have two companies. One of them is offering me FMC saying, well, I can give you a pipe with a heat transfer coefficient of 5. That's what we were using. Okay, or I can give you another pipe with a heat transfer coefficient of 1.5. That is going to save dramatically. It's going to reduce the appearance of wax in the line, etc. And basically, it's the type of insulation, the quality of this material that you have, and also the thickness of this material that you have. So I made the homework for you, and here is how it looks like. That's for 5 watts. That means a poor insulation or a bad insulation, and that's for the good insulation. Okay, bad insulation and good insulation for the temperature. Yeah. And you see that basically the advantage of having a good insulation is twofold. Basically, I can have a required pressure is less. That means that I will use less energy pumping, okay, which is a big advantage. I reduce from 90 something, 91, all the way to 75, 15 bar. And by that, let's calculate how much is that in watts. If you remember, I told you was the power of the pump was Q times delta P, right? And delta P, we said we had a saving of 15 bar and times the Q, and the Q is, okay, I closed it. Wait, could you tell me the Q, please? Is 18,000, something like that? The Q, it can be, let's say, at the inlet of the pipe, at X equals 0. What is the Q of oil? Uh-huh. 1596.2. That's a cubic meter per day, right? So I have to divide by 3, 6 times 24 to obtain by second. Yes? So how much is that? What is the power I need? That should be also in Pascal, so I should have this to 10 to the 5 Pascal. Okay, so some of you that can help me with the calculation, or I can do it myself, but let's see who goes quicker. 1 e to the 5 times 1 5 966. Yes. How much is it? 33. Okay. Divided by 600 times 24. Okay, that is in watts. So that gives me how many kilowatts? That will give me this divided by 1,123. That is in megawatt. Okay, the power is around, raw power is 0.28 megawatt. Okay, but remember, usually a pump is not actually 100% effective, but has an efficiency. And that efficiency is someplace around zero point 0.7. So the actual power is the hydraulic power, that's the hydraulic, divided by the efficiency of the pump. So how much is 0.28 divided by zero point 0.7, for example? That gives you 0.4. Okay? So half a megawatt pump, you're saving. Okay? It's a big saving. It's a big amount of energy that you're saving just by using this insulation. So you have to think about that part, and also maybe you reduce wax deposition, because the temperature now will be at the end of the pipe will be 40, and 40 is just a bit before this cloud point. So maybe you don't have any wax at all in the pipe. So maybe in this case it's like two advantages. I save a lot of energy that I don't need pumping, and I also avoid having too much piggy in the line. Okay, see that? So in that case, I will say we will try to squeeze my boss to go for this very expensive insulation. Okay, maybe some. There are some insulations they make pipe in pipe. So one pipe is outside, you have vacuum, and then you have the pipe inside. All kind of tricks, but this can help you. This analysis can help you to decide on that. And this power is so high not because so much of the delta P that's relatively low, but it's actually because of the rate that is huge. Okay, this rate is huge. Also, another thing on the exercise that you see the variation of the Q. Okay, see the Q that we are using now. The Q actually change is not anymore 15,899, okay, but actually you have 16, 16, so you have some variation of the rate of the local rate. This is because it's just taking into account the compressibility of the oil. You're in this undersaturated regime, but if you are in, if you're releasing gas, liberating gas, then it will be much more clear. Yes. Okay. So the homework, I want, for 1 kilometer interval, please plot also pressure and temperature, and make it nice. And if you want, you can do some other analysis on the, on the insulation. But that's the homework. Okay. So that's the saving in pump power by insulating better the pipe. Okay. And instead of buying, for example, a pump that is 3 megawatts, you can buy one that is 2.5 and you save some money. But you have to be also check how much this insulation costs, okay? Because you have 75 kilometers of pipe that need this insulation. So it might be very expensive, and at the end you prefer just to buy a bigger pump and get rid of the problem. Okay, so now we abandon now single phase liquid. Okay, I told you more or less everything that you can do with single phase liquid. Don't neglect it. You say, oh, we never have single phase liquid, but actually you have some cases, especially transportation systems, and it's extremely important to take temperature and pressure into account. Okay, and you know now how to calculate. One thing that we didn't discuss, and we are not going to discuss here, but you have to be careful, is non-Newtonian fluids, okay? And here we have some oil plus water mixtures. They display no Newtonian behavior. Actually, it's not proportional, the relationship between stress and displacement. And also some drilling muds, some oil and water emulsions. Okay, some drilling muds, and that we're not going to cover here, but just be aware that you have the other tool that you need for single phase fluid is non-Newtonian, and I guess you cover some of that in drilling, in your classes in drilling. Okay? So with that, you more or less complement your whole education on single phase. Okay, so now let's go to multi-phase. Okay, what happens when we have multi-phase? Multi-phase flow in wellbores. And now comes some fun. Okay, so remember that we have for every hydrocarbon, okay, or any composition, we have the phase diagram, okay, of reservoir fluids. And if the reservoir or the fluid is, so we have P and T, and if you remember, we have some lines that they define the envelope, okay, and this is what we call this green one, that's the bubble point line, okay, bubble point, and this is the dew point. Dew line, okay, and this one here, this guy here is actually, this is the critical point, and we have then this guy, this is temperature, okay, so this point here is the Crickondon term, and this guy here is the Crickondon bar. Okay. Now, usually for oil reservoirs, we are someplace, if the reservoir is undersaturated, we are here. Okay, that's initial reservoir pressure and reservoir temperature. And when we start, let me put it down. When we start flowing through the system, okay, from the wellbore, the bottom hole, let me use another color, maybe use this one. Actually, you have in the reservoir, you don't have much change in temperature, so it goes just down like this. So that's the PWF, okay, flowing bottom hole pressure. But then when you start flowing into the well and through the whole production system, then you are actually inside the envelope and you have multi-phase. Okay? Oil reservoirs, actually, you are to the left of the critical point, and gas reservoirs, you are to the right. Okay? That's oil reservoir, and in this case, just sure that we are producing the bottom hole pressure actually is undersaturated. Okay, but it might be that this point also could be inside the envelope. And then for these cases, for the gas, this one actually the critical point is someplace here. You have something like this, exactly the same critical point, etc. And then you have reservoir pressure is here. If you're producing through the undersaturated, then this is the flowing bottom hole pressure, and then you go all the way to P separate. Okay, and here we have, remember, we have these famous lines that what are they? Okay, these are lines that have constant quality. Okay, and the quality is equal to the mass of gas divided by the mass, total mass. Okay, so here is 1, here might be zero point 0.8, zero point 0.7, and so forth. Okay, and that allows you, depending where you are, that tells you, how much gas and how much liquid you have at that point. These are quality lines, what we call quality line. Okay, and let's see if we have time. Maybe on Thursday we'll use a simulator to generate this envelope. Okay, and we will see how pressure and temperature change along the system. By the way, did you use any process simulator to make this curve? No? Okay. You don't have a class about processing or thermodynamics? No? Okay. Well, we'll see if we have time on Thursday. I think we'll have time. So we can. And be also aware that in gas reservoirs, you might be passing through a condition that is called retrograde condensation. Okay, basically we have this critical point. Okay? And if you see these lines, actually they do something like this. Okay, that means that if you start here, that's your reservoir pressure, and it starts to decline, you will start up to this point, you will start getting liquid and more liquid and more liquid, right? Because you go from 1 to 0.8 to 0.7. But then if you continue going down with pressure, you at the end you'll start to revaporize, which is very strange. You'll start to revaporize until you might end up just with pure gas again. Okay, so that's called condensate, or retrograde condensation. So this plot is not, I think, from engineering, if you want to make calculations, really this plot, it doesn't help that much. But I think you always have to make it to understand your system. Okay? I don't think it gives you so much to say exactly which pressure to make calculations, but it gives you an idea where you are. So it's very, it's for education, it's extremely nice. Mhm. So usually now I ask you something. This is gas reservoir, okay, an oil reservoir. And this is made for a particular composition Zi. Okay? I make that plot, and if I change the composition, the envelope will look slightly different. Now I ask you, how is this the well flowing composition with time, okay, with depletion? If we have a well bore, okay, we come back to make well bores, to make wells. Okay, and we have here, so let's go maybe case by case. If I have the case, all of this is undersaturated oil. Okay, then I ask you, is the set, that means the composition of the fluid coming inside of the wellbore, is it changing with time? Is it a function of time? That means, is the envelope going to change? Should I change it? I have the points pressure and temperature along my system. Should I change this envelope? No, right? Because here this is a liquid, and all the liquid is coming into the wellbore. Okay, so basically every point that I sample here has the same composition, and if everything enters, I have here PWF is greater than the bubble point pressure, then basically my composition doesn't change. My envelope doesn't change. Okay, that's case number one. What happens now if I have undersaturated gas? That's where PWF is greater than the PF of the dew point pressure at reservoir temperature, and this is also at reservoir temperature. The composition is also constant. Okay, so the envelope remains exactly the same. Okay. Now I ask you, what happens if we have saturated oil? Okay, I'm going to copy the same diagram. Okay, and saturated oil, basically I start, because the pressure goes down, okay, close to the wellbore, so I start having some, here I have some, maybe some small bubbles of gas. Here I have more, and here I have many more. Okay? So I have, with time, when the pressure is going down, the saturation in this area, the saturation of gas is starting to go up with time. Okay, that means that I have more and more gas. Then the GOR starts to increase, right? The GOR of the well. So GOR also increases. And they have basically different composition, these two. And if I'm mixing oil and gas at different proportions, then the composition is also going to change. The composition entering into the well. Okay? So in that case, I should use also a different envelope to calculate. So Zi is a function of time. Okay? And also the same thing if you have, for example, coning. Let's copy exactly the same diagram. If you have a gas cap here, and then you have coning, that actually gas from the gas cap starts entering into the well. Let's make actually put that thing here, and let's copy the well so it won't be alone. Okay. For gas coning, the also the composition coming into the well, the Zi, is also a function of time. So be careful, like we make this plot and it's very easy to understand, but basically all of these lines might be changing depending on the system you have with time. Okay, so be careful. It's just to, to call your attention on that. Okay, but now let's paint, for this case of undersaturated oil, let's see what happens in the wellbore. Okay, for the case, I'm going to put it here, for the wellbore producing with PWF greater than the bubble point pressure at reservoir temperature. Okay, so I'm going to make my wellbore slightly bigger. And I'm going to put again my packer. Here and here. Okay, so big wellbore. So that's PWH and that's PWF. And let's draw here my phase diagram. T, P, yes, so now we are, let's say we are here, that's reservoir pressure. We are here, that's bottom hole pressure. And then we're going to go all the way down to P wellhead. Okay? So first, initially, in the wellbore, we have just single phase liquid. Okay? Here we have single phase liquid. After I start, exactly when I cross that point, when I cross that line, I start having gas coming out of solution from the oil, some gas liberation from the oil. So then I have some small bubbles of gas, and this flow pattern that I have, this already makes what we call, this is a flow pattern. It's how the phases of oil and gas arrange themselves in the wellbore. Okay, but this is what we call bubble flow. Okay, bubble flow because you have bubbles of gas going through a single, through the oil. If you continue going down this road, then you will see basically that these droplets start to become bigger and bigger. And they start actually to coalesce and form bigger droplets. This also we call some kind of bubble flow. And but if they at the end they continue coalescing, they continue merging together, etc., you start having what we call slug flow. That basically you have big pockets of gas that they are followed by a pocket of liquid, okay, with some bubbles behind. Okay, and that's what we call, this one here is what we call slug flow. Okay, I think I will need to put a bit longer wellbore. Okay, I'm going to move this a bit up. Okay, and now after, if I continue with that, I will have some flow pattern that is called churn, that actually have these big blobs of gas and the liquid, the oil around, and that's what I call churn flow. And at the end, actually, what is going to happen is that the gas is going to form a center core with some droplets of liquid, and the liquid will be just attached to the walls. Okay, the gas will be so high the amount of gas, and I will have here, that's what I call annular flow. Okay, and all of that complexity I can have in one well. I guarantee you. You say why so change so much? It's not out of the mind. You can have actually the whole change in different flow patterns along a well, and that causes different problems because you see, like, this one I can calculate. I have to calculate pressure drop. Okay, so I cannot make the assumption that all sections are the same. Actually, I have to subdivide, calculate what flow pattern I have in every point, and then make an estimation of the pressure drop. And that creates a lot of trouble just because of that we are looking at. So as for oil, any question? No? Okay, that's what happens. And now let's see what happens for gas. It's taking time, but I think it's important that we do it slowly to avoid confusion. Okay, for gas well, let's make it again a very big well bore, PWH. Okay, and I have again this phase diagram. So in this case, this point is to the left. Then we have here. Okay, so here I have reservoir pressure. I go down. This is PWF, and then I go in this direction all the way to PWH. And let's assume that you all the time have condensation. Basically, you have no retrograde behavior. So initially, you will have pure gas. Okay. Then you will have gas with some small droplets of liquid. And I call that, how do I call this flow pattern? So this is single phase gas. This one, this is called mist. Okay, it's like a mist, rocio, or is it the same in Portuguese? Rocio? Yeah, you have in the morning some mist. It's like when you use this vaporizer, spray, yeah, spray flow or mist flow. Okay? Then, if you continue going down, you continue increasing the amount of liquid, then the condensation of liquid, you will have another pattern that the liquid starts attaching itself to the wall, okay? And then you have a core of gas, just like in the oil, okay? Exactly the same as at the end of the oil. And you have some droplets of liquid, okay? That's what we call, how do we call this flow pattern? It's the same that for oil, annular. Then if we continue, then we are in trouble. Actually, we will have some pockets of gas and okay, some pockets of liquid, and that we call slug flow. Okay. So if you see, it's like the opposite. If we put one next to the other, then we will have the full range from going to full liquid to going to full gas. Okay, if we put one on top of the other. Okay, but basically that's what happens, and that's the complexity we're dealing with when we are talking about a multiphase. So this is what we call the flow pattern, or also called flow regime. That is basically the way how phases, basically liquid and gas, arrange themselves in the pipe. Okay, if you have bubble, if you have, and that depends on many on many things. That depends on many things, and we are going to just to hold that discussion on what it depends. But let's talk about what we really care. Okay, that is how. Remember, all that we are looking for is PWF. We have the available, right? And we want the required. We know already how it looks like for gas, how it looks for liquid, but how does it look like for this multi-phase guy? The TPR, okay? That's what we are looking for, the TPR. And actually, the TPR looks strange. It looks something like this, going down and then start to go up. That's how the TPR looks like for multi-phase. Okay? Strange. It doesn't just go up. It just goes down first and then go up later. And we are going to explain that a bit later in more detail, but just at this point what you have to see is that there are two very different regimes in this. So here is like gravity dominated, okay, area, and this is the friction dominated area, okay. And this one you can understand very okay. You remember that the pressure drop, okay, if we make the pressure drop total, is usually a sum of delta P acceleration plus delta P due to hydrostatic plus delta P due to friction, right? Let's neglect the acceleration now for a moment, okay, and let's look at these two. This one, the friction will increase if I increase the rate, right? Because you have this velocity squared someplace. So it makes completely normal sense that this goes up here. But what happens with the hydrostatic? Why? So the reason why here is that here is very big. It's somehow, this thing is is bigger in this region. So in this region, okay, delta P, let me bring this down. I think I already ran out of space. In this region, the friction, the delta P of the friction is much more important than delta P of hydrostatic. But in this region, delta P of hydrostatic is much more important than delta P of friction. Okay? And the reason why I will try to give you, I hope you understand, but if not, we're going to cover in detail later. Okay? But basically is that here I have, it's like the liquid is going very, very slow. Okay? So let's look at this point number one. Okay, point number one. The liquid is going extremely slow in the pipe. And when the liquid is going very slow, the gas actually is like it cannot go. Both of them like to walk to they are like two friends, okay? They like to walk together, okay, to any place. But when one of them is just going extremely, extremely slow, gas just okay, I drop you and I just go quicker. So because of that, the oil occupies because it goes very, very slow, and you have to carry a certain rate. Actually, that one shouldn't be here. It should be someplace here. Okay. Then the gas is going to go extremely fast. Okay. Velocity of the oil and velocity of the gas without the G, without the bar. Okay. And you see here the density. Remember that delta P hydrostatic is proportional to the density of this mixture. Okay, and here the density of this mixture is going to be very similar to liquid because gas is not going to wait for oil. So oil is going to go very, very slow and it's going to occupy the whole volume of the pipe. Okay, now when I look at another point here, actually oil is going much quicker. So gas is like it can go with it. Okay, I will go with you. It's like the gas is able to drag it up. So in that case, for point two, basically you have that. In that case, maybe it will be something like this, that the gas will start to go quick, but the oil is also going quicker. Okay, and at the end, okay, the density of the mixture will be something like, something in between the liquid, something in between the liquid and the gas. Okay, will be in between these two, and it depends really how fast goes one. In this one, I think I made a wrong kind of. It should be very small the velocity of the oil, and very big the velocity of the gas. And here they are more or less they are the same. And so that's what happens when you increase the velocity. Actually, the oil starts to go quicker, and then the gas can just catch up with it. When the oil goes very slow, the gas just drops it. Okay, you go too slow, I will go to my at my pace. Okay, a kind of simplistic explanation, but okay. So yes,
The last approach of cash is it for dry cash and wet cash?
this. What do you mean? This one?
Yes.
Yes. The only thing is that if it might enter, for example, the reservoir pressure might be also here, and then you don't have single phase gas. It will just come in right with mist. Okay, or even with annular flow. Okay, so it really doesn't matter where you start. That's to tell you, like the most extreme case, if you enter with single phase gas, but you could enter really with any point in this curve. Your reservoir pressure can be in any point in that curve. What will happen is that there will be some flow patterns that you won't have. Okay, for example, if you enter with too much liquid, you might come already in annular, and you don't have single phase gas or mist. You will have just annular and slug. Okay, so the point here to convey is that the curve looks like that, and that's because here is gravity dominated and here is friction dominated. Okay, when you start increasing the velocity, the gravity dominated goes down and then the friction goes up. okay, and you have a minimum, and that's the intersection that we're looking for. And that causes a particular problem, okay? That, just to call your attention, you can have, it is possible to have two intersections between TPR and IPR, okay, in two phase. And that's something that really causes a lot of problems. So if you see now, I painted intentionally, that's Q and that's PWF, and my curve will look like that. And what happens if my TPR is like this now? Okay, that's my TPR and that's my IPR. I have two intersection points. So which one nature, okay, which one the well is going to choose? Is the well, we want the well to be here, right? That's what we like. But really nature maybe choose to be there. We don't know. There is a long mathematical demonstration why which point is, but that's related somehow. If we make it very simplistic, this point here is called a stable equilibrium. That means it's like if you have a ball and you have a ball at the end, okay? And then if you move the ball up, it will always try to go back to where it was, okay? And this point is the equivalent, is what we call an unstable equilibrium. And that is the equivalent to do that, okay? If we move it, then it will tend to fall out of equilibrium. It's very difficult to maintain that point. And we will see, I try to explain in a very simple way why. So if in this point, for some reason, we have a variation of rate, okay, and now we move to the right, okay, to the right, let's say the rate is increased by some reason, okay, for some reason there is fluctuation, okay, you're producing the well, okay, and the rate is fluctuating up and down. Let's see that now it's increasing in this point. If it's increasing, then the required is more than the available, right? In this point, the P required is greater than the P available. Okay? Yes? So that means that the well, because of that instability, will tend to reduce the rate. Because just because the required is more than the available. Okay? And I will go, if I'm here, then it will tend to go back. Because I cannot bridge that difference. Also the same thing if I now for some reason now the rate goes down again. Okay? Here the required in this point, the P required is actually less than what I have available. Okay, so in that case, the well will tend to just increase the rate and go back to that point. So you see, everything that pulls that point to the right or to the left is actually exactly like this analogy. It will tend the well to put it back into the equilibrium rate. Clear? Yes. Now let's see what happens here. If I now put, the rate changes and it goes to this side. Here in this region, the P available is greater than P required, right? Than the TPR. That means actually that the rate will have to increase and increase and increase, and eventually I'm going to reach up to this point. Yes? If I make any change here, the well will end up working here. Okay, so that's why it's unstable on the right side. And on the left side, what happens if the point is here? Okay, in this region, the P required is greater than the P available, right? The required is this curve and the available is the other curve. So that means that the rate has to be reduced. So the well will reduce until it's shut in. It's not producing anymore. Okay? So And that's not just some theoretical explanation. That really happens in the field. So you really have these wells where you have these two intersections. So if it's operating here, you have to find a way to boost it, to increase the rate somehow, to give it a push such that it can reach this point. Okay? Because if for some reason the rate is reduced, you put it to produce, it comes to this point, then it stops producing. Put it to produce, stops producing. Put it to produce, etc. Okay? So you have to find a way. So that's also called to, so let's say to, so let's call this point 1 and point 2. And to change, to move from unstable equilibrium to stable equilibrium, we need sometimes what it's called flow induction methods. Okay? And there are all kind of things, all kind of methods, but basically I try to help the well somehow to increase the rate, push it past the first equilibrium point such that it will go to the second. And that's where I want to produce. Okay, we have 1 hour and a half left. That's my computer, what he's saying, 1 hour and a half. Okay. Okay, so let's continue for 10 more minutes and or let's see. Okay. So the first some name that you have to remember was Gilbert. Okay. In 1954, he published a paper where he presented three things. He presented first IPR, and he presents some information about the curve, how it looked like, how it would change with time, how it looks like for water, what happens when you change the gas liquid ratio. Then he went to the main part of the paper that was to show how this TPR looks like. Okay, to show the curve, and he showed a way. Actually, he proposed a way, and maybe we'll make a comment maybe tomorrow, or I think better on Thursday. So how his method works, because it's really brilliant, and you don't need all of these complicated calculations. But the thing is that it's not very accurate. But it was a very nice way to solve this problem, and he also talked about choke. But here he presents this complexity that actually the TPR looks like that, going up and down, and he gave some simplistic explanation why it looks like that. That is also very, very powerful. Um, yes, what I wanted to tell you now is what happens with this curve. Okay, so that's called PWF and rate, and you have this IPR, and you have, for example, this TPR. This TPR usually is for a fixed gas liquid ratio. Okay, fixed. GLR means gas liquid ratio. Okay, certain GOR. If you have no water, that means certain GOR. What happens when you reduce this gas liquid ratio? Sorry, when you increase it. When you have more gas in the tubing. If you have increased the gas liquid ratio, okay, then what happens with the density of the mixture in the tubing? Goes down. And so what should happen with the curve? How it should look like? Something like this. Okay, gas liquid ratio 2, where gas liquid ratio 2 is greater than gas liquid ratio 1. Okay, so you're going to get, so that's, we are going to talk about gas lift a little bit at the end of the week, but that's actually the philosophy behind gas lift, that you want to increase the gas liquid ratio such that your required will be displaced going down. Okay, but when you inject too much gas, when the gas liquid ratio, so it will start or continue reducing and reducing and reducing, until one point where it will start actually to go back up again. For example, the gas liquid ratio 4. Okay? So it will give you more and more and more production, but at some point it will start to go back, less and less and less production when you start increasing the gas liquid ratio. And that's because this one becomes the delta P. So let's see, gas liquid ratio of 4 is greater than gas liquid ratio of 3, greater gas liquid ratio 2 of 1. So here in this point, delta P hydrostatic becomes smaller than delta P by friction. Okay, so all the gain from here to here, from 1 to 3, you were gaining a lot by adding gas to the tubing. You were reducing quite a lot the density of the mixture. But after I went from GL3 to 4, actually you went, that's the minimum that you can get. That's the, and then the friction starts to making a big effect. So that's why you have a change of trend, okay, in the equilibrium point. Change of trend in the equilibrium. So if you plot the equilibrium rate QO at equilibrium versus the gas liquid ratio, you will see it does something like that and then goes down. Okay, you have a maximum, and that's the optimum gas liquid ratio where you want to operate. Clear? Yes? So now I'm going to show you just to, I think we have an exercise and definitions, but I think you're tired or you can go for another 10 minutes. No? Too much? Okay, let's try. So that's the curve that Gilbert showed in his paper, his famous paper of 1954. You see, let's try to make it bigger to see what it shows. Basically, that's the PWF, the intake pressure to the tubing, and that's the rate. Okay, and you see it goes down and it goes start to go up. And that's for a fixed gas liquid ratio of 5. Okay, but when you start decreasing 4, 3, 2, and 1, the whole curve is just displacing and going up. Okay, so you get more when you start reducing the gas liquid ratio, you get more and more and more pressure drop. Okay, that's from Gilbert paper from 1954. Hmm? Yes, so let's summarize. Okay, what have we done today? Because I feel like you're tired, and if I go with flow patterns, you are going to be a bit stressed, I guess. Okay. Today we looked at one exercise just to to cement your knowledge on liquid flow. We said it's a pipeline of oil. We have to take into account first the compressibility, okay, because the rate in standard conditions is not the same as in local conditions, and also we have to take into account the viscosity change along the pipe. So for that, I told you we are going to use the same expressions we did last class. We're going to perform the integration from the point where we have the pressure, which is the separator. We're going to calculate all properties there, and then we're going to say, I calculate the pressure here, assuming that all properties are constant in between. Then after I'm here, I move also upstream, upstream, upstream. Aguas arriba, okay, counter current. But with temperature, actually it's the opposite. I have the temperature here and I have to move co-current, con corriente. And we had a very complicated equation, differential equation, but it's liquid. We could do a lot of simplifications. And at the end, we end up with an equation that really doesn't depend on pressure. It only depends on mass flow, which is constant along the pipe. It depends on this heat transfer coefficient that is also constant along the pipe. and the diameter of the pipe, which I assume is also constant along the pipe. And then we were doing calculations. We did temperature from the wellhead, okay, from the, not the wellhead, but from the inlet of the pipe all the way to the separator with this exponential equation. And we did pressure calculations the other way. Okay, we did from the separator all the way to the inlet of the pipe. Okay, and for that there were a few tricks. You had to use this table interpolator that I gave you. I hope you know. I think it caused more confusion that it saved you time. Uh, but then important to show that exponential in temperature and in pressure actually is not linear, and that's what we were doing last day. Okay, that was just linear. You were using just one equation for the whole pipe, for the whole tubing. And that's why it's important to make integration. Then I compare, it's very nice to compare the different insulation, which insulation to choose. A better insulation is more expensive, but can save pumping power, and it can also save, pigging. And then we went to multi-phase, and actually we say, well, what you really have in every well, almost in every well, you have multi-phase. Okay, because you might start or not where you have single phase under saturated liquid, under saturated gas, but you, no matter what, due to the reduction of pressure and temperature, you go inside the envelope, and that's a big problem. Okay, you start having liquid and gas, and that causes some issues. First, composition, well, that's not so important, but first, this causes a different arrangement depending on the amount of gas that you have and the amount of liquid that you have, a different arrangement of the phases inside this pipe. If you have a little bit of gas, then it will organize it in bubbles. If you have a bit more gas, then it will start to coalesce and form big blobs or bigger bubbles. Then you have slug flow. Actually, you have batches of liquid and batches of liquid and batches of gas. And then at the end, all of them will merge up and make annular flow. You have a core of gas and you are surrounded by a film of liquid. For gas, similar. Gas, you have mist flow that you usually don't have in oil wells. Then you have annular, slug, and etc. And then we talk the curve is something that you have to take today. That you wake up in the middle of the night and you have to say, this is what I learned today. The curve, the shape. Okay? When I ask you how does it look like, even eyes closed, you have to say like that. Okay? Now it's not anymore like this or like this, but it looks like that. And that's the biggest learning. Okay? Why you have this balance, and we will see later why is that, but you have hydrostatic friction here. Friction is more important. Here, gravity is more important, and it has to do with these two guys that want to be all the time close to each other. Okay? Here, one guy goes very slow, so liquid leaves it behind. And here, actually, they are starting to go together at the same pace. And yes, and we are finished. So see you tomorrow.